Ajisha
So
started.
good afternoon, class. Please,
Jesus.
everybody, Razak, I'm going to make you a co-host. I'm making you a co-host so you can make sure the class is well muted. Please, as part of education, you must know that whenever you enter a platform, you mute yourself.
Are you doing no class?
Abrazak, you are the co-host. Please make sure that the class is muted. When anybody that disturbs my class, I'm going to remove the person from the class. And please tell people in biochemistry that if they did not attend this class, the attendance remains 0 with me. If you have anybody, is there anybody in biochemistry here?
I'm not a biochemistry student here.
Okay. Please.
Yes, ma, we are here, ma. I'm one of them.
Please make sure your friends are here too.
Yes, we are all here, ma.
Okay, fine, good. So let's continue with the class. Attendance is this is going to be the last class for this section I'm going to have with you. Tomorrow, Professor Faminoni, Professor Sheku will start with you and finish the last section, last part of the course. Then after which we're going to have a comprehensive test. So I want you to make sure that all the classwork that was given, you participate. And also to her, she's going to be having hybrid. She can have physical tomorrow, and she mostly have others to be online. So make sure you attend her physical class. At least first class should be compulsory for you, so that she will know that you are part of the students. If on the first day you're not available and there's attendance taken, it will, even if online, she might not take you serious. So I'm giving you that as a clue. So make sure you are available. Okay, so in the last class, we were talking about synthesis. So we're going to still continue on that synthesis today. Now, like I said, make sure you connect with all the classwork. Okay, slide. I know you have the slide. So we're going to go to slide number 21, where we're going to talk about synthesis of 1-alkyl naphthalene, meaning naphthalene that has 1 alkyl. That alkyl can be methyl. It's alkylated naphthalene at position number 1. Okay, right. So in this reaction, we're going to use benzene and succinic anhydride. In the presence of a Lewis acid, which is aluminum trichloride, we are forming 4-oxo-4-phenylbutanic acid. So using zinc, a mercury, and HCl. Now, if you remember when we are talking about carbonyl, you realize that this is clemensine synthesis, where my carbonyl, that's ketone functional group, is changed to aliphatic. So zinc, a mercury, and HCl is supposed to take away the oxygen from my ketone to form a cyclic or alicyclic compound. In this case, the alicyclic compound. So what it's doing is just taking away the ketone functional group. Okay, that's down. Whenever you're doing a reaction like this, whenever you add a reagent, ask yourself, what is the essence of this reagent? That reagent is doing a particular thing. So always look at the place the reaction is taking place, which is actually the functional group. The functional group that is reactive. It will help you not to cram, but to understand. So now when I'm talking about, after that, I'm going to add sulfuric acid, dehydration. When water is being removed, there is also cyclization, because we are going to close the ring, and we form 1-tetralone. Now, using greener reagents in the presence of water, you can see where that's essence of greener reagents. Its form is to alkylate. Then we have alkylated hydroxyl naphthalene, which will also, then the water will partially remove to form my 1-alkyl naphthalene. So the major reagents we have here is Lewis acid, clemensine reagents, then dehydration and greener reagents to form your 1-alkyl naphthalene. So if exam, the question is formation of alkyl naphthalene, then you know that you're going to use this method. But if you ask one name method, at times they can even talk about using Howard synthesis. Okay, use equation alone to show the synthesis of naphthalene. This is also, if you look at it, it is still the same alkylated naphthalene. So both methods are forming alkylated. And in that method, you realize that we are still using virtually the same reagent, Lewis acid, in Howard synthesis. We were using Lewis acid, the same thing, virtually the same thing. So both methods are something you can relate to. If you know one, you know two. Howard's method and this 1-alkyl naphthalene synthesis are still using Howard the same reagents. Difference is when you're talking about greener reagents in synthesis of 1-alkyl naphthalene. Okay, so now what are the reactions of naphthalene? Reduction, whenever you're reducing, what is happening? If you look at naphthalene and reduction, you realize that one of the hydrogen is removed. Reduction is opposite of hydrogenation. Hydrogenation is addition of hydrogen. Okay. Now, when you're and remember, hydrogenation is a reductive reaction. So reduction is hydrogenation. Now, whenever you're reducing, you're adding hydrogen. And whenever you add hydrogen, double bond becomes saturated. So in this reaction, we've added hydrogen using sodium in ethanol. Now, to form 1-dihydro, meaning the carbon at that point the hydrogen has been removed. We're having 1,4-dihydronaphthalene. We can also do reduction using sodium in isoamyl alcohol. Then we're going to have 1,2. So whenever you're using, please, course rep, please take charge. So all these things we are doing is reduction. Reduction is addition of hydrogen here. So when we use the sodium and ethanol, we are just adding 1 mole of, who is doing this? So we are just adding 1 mole. So we're going to have just 1,4. When we are using sodium in isoamyl alcohol, we are going to have 2 moles. So that's why we're going to have 1, 2, 3, 4. So when you are doing hydrogen in nickel, which is dehydrogenation, dehydrogenation is a reductive reaction. Every of the hydrogen will be removed. So we're going to have decahydronaphthalene decalene. Okay, decahydronaphthalene, which is also called decalene. So whenever we are using sodium in amyl alcohol, we are forming tetralene. Tetralene is 1, 2, 3, 4 tetrahydronaphthalene. Why decalene is decahydronaphthalene. So these are the reduction. So at least you'll be able to know reduction reactions of naphthalene. One at least be able to know one. But if you're giving a specific reaction and the presuming you're giving a naphthalene that forms 1, 2, 3, 4 or the tetralene, and you're expected to tell us the reagent, you should know that that one is using isoamyl alcohol. Okay, but when I'm removing all the double bond to form the decalene, I'm using hydrogenative reaction. If I don't use hydrogen in nickel, I can also use hydrogen in platinum or palladium, because every hydrogenation reagent can do this work. Okay. Oh, I think okay. Sorry, I think I was, because I'm using my laptop and yeah, so that's why I was working on laptop and I was not linking it up to the slide. Sorry. So this is reduction. In reduction, we can have sodium in ethanol, sodium in isoamyl alcohol, hydrogen in nickel. It can also be hydrogen in platinum, hydrogen in palladium. So all these are how to do reduction. When I'm using sodium in ethanol, I'm just adding 1 mole of hydrogen. When I'm using sodium isomeryl alcohol, I'm using 2 moles. So when I'm using hydrogenation, that's hydrogen in nickel, platinum, palladium, every of the double bond changes to saturated. So I'm going to form a decalane. Tetraline is sodium isomeryl alcohol. Please, I want you to know the differences. This is reduction in naphthalene. Okay, we also have reduction in oxidation in naphthalene. Oxidation, remember, in oxidation, you're going to always primary form a ketone, secondary form aldehyde. Now, whenever I'm using chromic acid acidified chromic acid, acetic acid, and chromic acid, well, I'm going to form 1,4-naphtha-quinone. So when I'm using ozone, ozonolysis is going to form phthalate. Why oxygen in phenoxide is going to form phthalic anhydride. Then normal oxidation is going to form, that's potassium, acidified potassium is going to form phthalic acid. So you should be able to form, how can my naphthalene move to phthalic acid? Remember, when we are talking about preparation, right? We talked about how I can form my phthalic acid from naphthalene using oxidation. So this can also apply here. So you should be able to know, you should be able to know somebody is disturbing my class. So you should be able to know at least 2 reactions of oxidation. Naphthalene and under oxidation. If you don't understand it, remember anyone, or remember oxidation with permanganate, acidified permanganate to form phthalic acid. At least know one of the oxidative reactions. Okay, so we're going to use this slide. Naphthalene can undergo electrophilic substitution reaction at position 1 and not 2. It can undergo at position 1 and not 2. Carbocation is more stable at position 1 than 2. So we are talking about whenever naphthalene is undergoing reaction, that is only position 1 that is much more viable and not position 2. Okay, so we're going to apply it in the reactions now. Look at this reaction. So now we can use nitration reaction. Remember, just like benzene, naphthalene must go with conc nitric and conc sulfuric. Remember, I told you in the class that phenol cannot go with conc because it's already activating. Hydroxy group is an activating group, makes phenol highly reactive. So it does not go. You can even react at temperature as low as 20 degrees because it's already reactive. But benzene must be conc nitric and conc sulfuric acid. In that same way, when I'm nitrating naphthalene, I'm going to use conc nitric and conc sulfuric, just like we did in benzene. Whenever I want to sulfonate too, sulfonic acid can occur in 2 temperature, 40 and 180 degrees. Please check in 213, we talked about temperature of 100 degrees and temperature of 40 or 60 degrees. Check it out. So there's a difference between naphthalene and benzene when you talk about sulfonation. Okay, but their product is the same. So whenever you're forming naphthalene 1 sulfonic acid, it must be temperature of 40, higher temperature of 180, you're going to form naphthalene 2 sulfonic acid. Chlorination, the same thing, virtually position 1. Remember from the previous slide, you see that position 1 is much more stable. So any reaction that you know about benzene is applicable here. But the most important thing here is that the only position 1 is much more stable in the reaction. So you should be able to know the electrophilic aromatic substitution reaction in naphthalene. You should be able to know them with knowledge of the one we did in benzene. This should be an easy one to deal with. Now, the effect of activators, right? Activating group direct electrophile to the same ring. Okay, activating group direct up. Remember, if I have like activators and electron donors, amine, okay, amino group, hydroxy group, carboxyl and alkyl, they're all electron donors. So they're activators. So whenever they want to direct, they're going to direct to the same ring. Remember, they are auto-para directors. So direct position 2 or position 4, which is the auto-para position. So like it applies in benzene, so it applies here. So there's no big deal. Okay, electron withdrawing. Electron withdrawing, the activators, they direct to the other group. So now the essence of this is that if I have a compound that has hydroxy group on position 1, so the incoming reaction, maybe I want to nitrate, is going to go to position 2 and 4. But if I have something like NO2 on that position 1, it's going to direct to the next compound, not to the same compound. So activators are going to direct on the same compound. The activators are going to direct to this other ring. We have 2 rings. So activators maintain the ring where they are, while the activators transfer to the next ring. It's going to be applicable in these reactions we are doing now. So look at this. I have hydroxy group already on the carbon, on the first ring. Now, because I want to nitrate, my nitration will be at position 2 or 4. And I have NO2. Okay? If I have NO2, if I want to now see this, look at position 2. Now my hydroxy group is on position 2. If I want to nitrate, my nitrating will still go to position 1 on the same ring. On the same ring. But if I have NO2 on position 1, I'm going to go to the next ring. I'm not going to have any product on the same ring. So the essence is that I have to know whether the reactant is activator or deactivator. Whenever a ring is bearing activator, that ring is anything incoming will be directed to the same ring, auto-para. If the deactivator is going to direct to the other ring, the same auto and para. The same auto and para. Okay? Unlike benzene, the activators is going to be meta directing on the same ring. But this one, the activators are going to be to the other ring and auto para. I hope that's clear. So we'll go to the next compound, which is anthracene. While naphthalene is 2 benzene rings, anthracene is 3 benzene rings. Anthracene is a solid polycyclic aromatic hydrocarbon. It's a solid polyaromatic hydrocarbon. I told you about what is aromatic hydrocarbon, polyaromatic hydrocarbon. Aromatic hydrocarbon is what you enjoy whenever you're eating your suya. So if you're a suya lover, make note that what you're dealing with is polyaromatic hydrocarbon. So take it easy. Okay, when this is a season of roasted corn, no wonder that roasted corn at times when you eat it, if you are having cough, it aggravates it. So why? Because you are consuming polyaromatic hydrocarbon when you're taking your roasted corn. So always apply caution when you're eating those. So like it's a component of coal tar. So that's a story you need to know. So how do I synthesize anthracene? Number 1, using benzyl chloride. Benzyl chloride. If you look at the reactants we are having, we can see we have 2 benzyl chloride. So, but their position are different, right? Okay, now these 2 benzyl chloride in the presence of Lewis acid, there's going to be closure. The ring will be closed.
Hello, ma. This live is not showing.
Sorry. Because I'm using both phone and laptop, so I'm not sorry about that. So we are using benzyl chloride, 2 benzyl chloride in different positions. Okay. Now I would have said that this other one was fisted, but if I want to talk about position like that, I take the same position. But remember, all the size of benzene is equal. Wherever I start, becomes my carbon number 1. So in the presence of Lewis acid, the ring is going to be closed. And removal of hydrogen is what? Dehydrogenation. So when I dehydrogenate, Then I'm going to close up the ring and I'll remove the hydrogen in the cyclo, in the middle ring. Now, if you look at that, meaning that what I just added is 2 carbon, because I have two ring already. So I have, what I added was 2 carbon, and that carbon came from benzyl. Okay, from methylene chloride. The methylene chloride in the aromatic ring is what gave me the 2 carbon. And when I dehydrogenate, I form double bond in the methylene because other ones are already aromatic. Okay, so that is my anthracene formed. Very easy. Using Friedecraft. So I can synthesize my anthracene using what? Friedecraft reaction. I can also use another reaction called Elb reaction. Elb reaction is when you form your benzene using orthobenzoyl toluene, toluene, or orthomethyl benzophenone. Under pyrolysis, I form my anthracene. This is one of the simplest reactions you can think about. This is the only method that is very, very long, sort of. So in this reaction, I'm synthesizing from naphthoquinone, 1,4-naphthoquinone. Remember when we're talking about oxidation of naphthalene, I'm going to form 1,4-naphthoquinone. So with this 1,4-naphthoquinone, using 1,3-butadiene, okay, I'm going to form a compound which will undergo oxidation again to form 9,10-anthraquinone, which under zinc form anthracene. The above method shows presence of naphthalene in anthracene. Remember, in anthracene, we have naphthalene with added benzene.
The slide is not catching up now.
Oh, shit. Okay, I think I should be using this slide instead of using my laptop so that I will correlate. So, sorry, in this reaction, we are using 1,4-naphthoquinone with 1,3-butadiene. Okay, so we are going to form an intermediate.
I don't show. Why don't you? I don't even know.
I'm trying to look for somebody that can remove. Please, Razak, help me monitor the class. Okay, 1,4-naphthoquinone plus 1,3-butadiene is going to form an intermediate, which under oxidation is going to form 9,10-anthraquinone, which with zinc will form my anthracene. So with this reaction, you can see that, remember, 1,4-naphthoquinone is the oxidation reaction of naphthalene. When you oxidize naphthalene using chromic acid and acetic acid, you're going to form 1,4-nitroquinone, which will react to 1,3-butadiene until undergo oxidation, and under zinc will form your anthracene. So we've talked about the first method, second and third method. Okay, now this is another method that you can use to synthesize which is the last method we're going to talk about in this reaction or preparation of anthracene. In this reaction, I'm going to use benzene and phthalic anhydride under Lewis acid, an intermediate will be formed, which will dehydrate to cyclize. And dehydration, what I'm doing is I'm closing up the ring, okay, to form anthraquinone, which under zinc, in the essence, this zinc is just doing the same work that we'll talk about when we're talking about cleansing synthesis. Okay, it's virtually doing the same work. That's the same thing that happened in the previous slide. 1/910 the anthraquinone with zinc form anthracene, meaning this zinc is going to take out all the double bond and then dehydrogenate, and then dehydrogenate the compound to form double bond. Okay, so in that same case, that's the same thing that is happening here. In this, we are using phthalic anhydride, Lewis acid. So the presence of dehydration, sulfuric acid, take away the water to form a ketone, because already there's a ketone in the first compound from phthalic anhydride. So in the presence of zinc, the 2 ketones is going to be removed and dehydrogenated. So reactions of anthracene. just like we talked about in reactions of naphthalene, we are talking about reactions of anthracene. These reactions of anthracene, if you look at it, you can understand that in my chlorination, I'm going to use chlorine with tetrachloride. Tetrachloride is going to be the solvent of the system. Then in my reduction, I'm going to use sodium in ethanol, just like what we use in when we were talking about reduction of naphthalene. The same thing happened in reduction of anthracene, sodium in ethanol. And in another reduction, I can also use, okay, we can see Friedel-Crafts reaction where we use ethanol chloride with Lewis acid to form a ketone on top of carbon number 2. And if you look at all the reactions are occurring either on the second ring or the first ring. Second and the first ring are the place we are having this reaction, and predominantly is the second ring. Look at when we are doing our nitration. When we are doing nitration, we are using acetic acid, acetic anhydride, and nitric acid. There's nothing like concentrate, that we are not using any conc sulfuric and conc nitric. We're using acetic anhydride as our acid portion, catalyzing the reaction of nitration and nitric acid. So if you be able to understand the difference of nitration in anthracene and nitration in naphthalene. In naphthalene, we are using conc sulfuric acid and conc nitric acid. While in anthracene, we are using nitric acid that is not conc and acetic anhydride. And my nitro group is going to be attached to the second ring, the internal ring. And when I was doing my Friedel-Crafts acetylation reaction, my ketone functional group is formed in that second ring too. When I was doing chlorination, the same thing happened. Okay. Now, this is another thing another reaction we're talking about is sulfonation. In sulfonation, what we need is just sulfuric acid. And sulfonation, unlike others, is the product is formed on ring 1. So these are the things you should be able to understand. Now, using the oxidation, sodium chromic acid, Na2CR2O7, you're talking about oxidation, acidified. So with sodium heptaoxochromate and sulfuric acid, you're going to form chromic acid. So chromic acid is what virtually does oxidation to form a ketone on ring number 2. So these are the things you should be able to know. You should be able to know, I think, 3 or 4 reactions of anthracene and that of naphthalene. Then the next compound we're going to talk about is anthraquinone. Remember, this anthraquinone is what you virtually see at times as an intermediate when we are synthesizing anthracene. It was an intermediate. So we want to know about this anthraquinone. Anthraquinone is a precursor to dyes. Okay. Plastics such as polyvinyltoluene can be dropped into anthracene to produce a plastic syncynator. Okay, so anthraquinone is a very important chemical in the industry. Okay, so anthraquinone, okay, is a precursor in dyes. So the essence is that this anthraquinone is very useful in the industry, especially plastic industry. Then we'll talk about phenanthrene. Difference between phenanthrene, you can see phenanthrene has 3 rings, but the arrangement is what differs phenanthrene from anthracene. While anthracene is linear, phenanthrene is angular. Okay? So how do we synthesize? This is phenanthrene. Anthracene is linear, while phenanthrene is angular. But how can we synthesize this phenanthrene? Just like we did in anthracene, we talk about synthesis using Howard method. In naphthalene, we talk about synthesis using Howard method. So it means that I can use Howard method to synthesize my anthracene, my phenanthrene. I can use it to synthesize my anthracene. I can use it to synthesize my naphthalene. So it is my duty to go and do my assignment. What is different between synthesis? What are the difference between the three syntheses? Now, something is very common in all the syntheses. Let's go back. Something is common in all the syntheses. And look at what is common in all the syntheses. When you're talking about synthesis using Howard method. I want to go back for you to understand. Okay, now, when I'm doing Howard method of naphthalene, what I'm using succinic anhydride. But in that case, I'm using benzene. Okay? Now, let's see when we are synthesizing anthracene, whether there is any sign of Howard employed. Now, the one that want to look like Howard is this, but not Howard. The one thing I want to bring out in synthesis of phenanthrene using Howard method is that in naphthalene we use benzene and succinic anhydride, while in phenanthrene we are using naphthalene and succinic anhydride. So because I need just an additional ring, now succinic anhydride is going to give me additional ring. That's why in naphthalene, I have one ring in benzene. So I added succinic anhydride to give me additional ring. Why? Okay, because in phenanthrene, I need 3 rings. So I cannot use benzene. Instead, I'm using naphthalene, which is already 2 rings. So succinic anhydride is going to give me the additional ring. So when I get the succinic anhydride, with Lewis acid, I'm going to connect the anhydride to the ring. Remember, I just want additional 1 ring. So I'm going to get that succinic anhydride using Lewis acid. So using Clemmensen reduction, I'm going to take away the ketone functional group. Then by dehydration, okay, I'm going to remove the hydroxy group and the ring will cyclize. Then further Clemmensen reduction is going to remove another ketone that is there, and I'm forming my phenanthrene. So this is very simple. Virtually what I'm doing is Clemmensen, Lewis, and dehydration. Whenever I want to remove ketone functional group, I employ Clemmensen reduction. Whenever I want to connect my 2 reactants, I use Lewis acid, aluminum trichloride. Whenever I want to dehydrate, I use punk sulfuric acid to remove the water. And whenever water is being removed, the ring will be closed, cyclization will occur. So that is Howard method. So I think it's easier for you to understand Howard method in naphthalene and Howard method in phenanthrene. With that, you should be fine. Because in terms of anthracene, you can use any of the simple method that you can easily relate it. Okay, these are the reactions of naphthalene, phenanthrene. Now, just like other reactions, naphthalene can also undergo halogenation. It can also undergo halogenation. Now, it can also undergo reduction. Reduction is sodium, okay, in C5H11OH, that's pentanol. So it can also undergo oxidation using chromic acid. Okay, heptaoxochromate, chromate plus sulfuric acid is going to use chromic acid. In that, now if you look at all the reactions, see virtually that is this second ring that is always reactive. It's the same thing that happened in anthracene is happening here. So whatever that is happening in that particular ring too. So oxidation is going to form carboxyl functional group because that ring is going to cleave to give us acid. Then another chromic acid in acetic acid is going to give us ketone. The ring inside is going to form a 2 ketone functional group. Why if you're using acidified chromic acid, it's going to form carboxylic acid. So I want you to understand the difference in the reactions, but at least you should be able to know the reactions of naphthalene, and the reactions of anthracene. Okay, why do we need polyaromatic hydrocarbons? Why do we need polynuclear aromatic hydrocarbons? Why do we need them? Why are they essential? What's the essence of them? You know, today is my last class. I don't want to remove anybody. I don't want to remove. Please, whenever you enter a class, it's a civil, okay? For you to mute yourself, it means you're what you're on. It means you're educated, you're learned. You can't just enter a platform and you're late and your people are hearing your voice. It does not make sense. Please learn that wherever you are and you're on online program, you're not the speaker. Please mute yourself. It helps you. It makes you to command a whole lot of respect because it means that you are educated. Being a graduate does not make you educated. It's some of these things that make people like, this girl, this boy, I think she's a graduate. Not because you have certificate, but because of the life you exhibit. So make sure you know how to carry yourself very well whenever you come to things like that. Because you're trying to tell people what you watch or where you're coming from. Okay, so I know you have questions. So you're going to ask any question you want to ask as long as this course is concerned. Okay, ask your questions, and if you don't understand how to answer some questions, please be free to ask so that you can be well guided. Because some of you, the problem you normally have is not about knowing the question or knowing the answer, it's how to approach it. At times you can be answering a question, you don't know that you're going off point, the lecturer is smart. By the time lecturer reads 1 and 2, even if you want to make sense in number 3, there's no grace, no patience to get to 3. The person will just give you 0 and move on. So that's why it's very, very important for you to know how to answer questions. Whenever you're in an exam, don't answer question because you want to impress your lecturer. You want to know that this person should know that I read this course very well. Don't go and you ask you set a question for yourself and you answer to show that I read, but the part I read did not come. So it does not make sense. Just make sure you understand the question and know how to tackle it. So why do we need polynuclear aromatic compound? Why are we even studying them? If they're harmful to our health, why do we need them? Like naphthalene is very useful in preparation of dye, plastics, pigments, in some pharmaceuticals and pesticides. Now, the essence is that's why it's very wrong. Okay, when you talk about dye, they said it's better for us to use food color. No, dyes are colors. So they said this is food color because other dyes are not healthy because of the presence of these polyaromatic hydrocarbons there. Okay, some pigments are colors. Now, that one of the reasons why plastics are not good is because of this naphthalene. You can see they are being used in manufacturing of plastics. So that's the problem we have. Okay, anthracene is also used in dye, in pigments, and as a diluent for wood preservatives. There's some preservative or some of them they spray on wood, and whenever they spray that, you can't be able to withstand the air that comes from that place. It's because of the presence of anthracene. And some of those, that's why you see some people that are working in such companies having problem like liver and kidney problem because of all these polyaromatic hydrocarbon they inhale. That's the problem of paints. All these pigments and dyes are also often used in paint, and that's why they are very, very harmful. So that's why people that normally work in paint industries, most of them don't live long because of all the accumulation of what they inhale, which are polyaromatic hydrocarbons. So we also have fluoroethane, fluorantine, which is also used in dye. Fluorine is also used in dye. But look at all the polyaromatic hydrocarbons. Something is common. Pigments. pigment, all of them. Pigment dye. So that is why we are talking about colors. They say, are you using food color? People advocate for food colors. Turmeric is a color. Call them. Zobo is color. Beetroot is colored. Some of these things are natural colors. Okay, we also have other natural colors. But that we also, these ones are called synthetic colors because of polyaromatic hydrocarbon. So to be able to give us at least one, even if they say the uses of a polyaromatic hydrocarbon, something is common: plastics, pigments, and dyes. So it's something you can easily talk about. You should be able to relate it with each of them: naphthalene, anthracene, fluorine, phenanthrene, pyrene, and sulfs. Okay, so that's a summary of polyaromatic hydrocarbon. Ask your question before we go for classwork, which we're going to end the class today with. Remember, the story is your classwork we submit online on Google Classroom, and submit it before the time of class elapses. So as we're in the class, when I talk about the classwork, you write it, you snap and submit on Google platform. Some people that will come and tell me that, it's not accepting. As long as the deadline is over, it might not accept. And if you don't have Gmail, you might not be able to log on. So make sure you download the app and do the assignment. So if there's any question, I'm available to, and the floor is open for your questions. Like I said, I'm going to inform Professor Chiku because she's going to take over from tomorrow, where she's going to be talking about organic reactions. She's going to tell about if we don't have questions, should I ask my question? Okay, I think we have a paper and a biro with us wherever we are receiving the lecture. So let's go for our question. Question number 1. Using Howard's method, show the synthesis of naphthalene and phenanthrene. That's question number 1. Number 2. Give examples of reactions of, give 5 reactions of naphthalene and anthracene.
Ma, can you repeat the first question?
Okay, using Howard's method.
Okay.
Using Howard's method, show the synthesis of naphthalene and phenanthrene. Okay, then
Anthracene and phenanthrene.
Phenanthrene and naphthalene and phenanthrene. Naphthalene and phenanthrene. So second question.
Yes, ma'am. The second question is give 5 examples of reactions of naphthalene.
Reactions, yes. Electrophilic aromatic substitution reactions of naphthalene and anthracene. So now, as soon as it's 5 minutes past 2, because we still have time. Please, cause respect the attendance. We still have time. We have over 10 minutes, at least 15 minutes, you'll be able to solve this question. And if you copy, I will know. So your time starts now. Let me put the question on Google Classroom so you can finish and submit.
Hello, Ma, are you there?
I'm here. What's the problem?
Are you going to resend the link for that Google form or the previous one?
I just go on now. Don't you have Google Classroom? No worry, I'll assign it. I'll send it to you.
Okay,
Ma,
ma.
please, the first question. Our network is bad.
Using Howard's method, show the detailed synthesis method of synthesizing phenanthrene and naphthalene.
Ma, please, the second question.
Using 5 examples each, show the electrophilic aromatic substitution reactions of naphthalene and anthracene.
For example, for reaction now.
What's this? So, Your time expires by 2 o'clock. But that thing is very simple. It's not open test I'm giving you. But even if I say you should not copy, you still copy. There are people that are not in class, they will not write it. So it's only people that are in class that can write it. That's the essence of it all.
Ma, please, the link.
I'm sharing the link. I'm sharing it on your platform now. Okay, so I've shared the link. So if you're done, snap and send. Some people are complaining that they've not been able to log in. What email do you use? Are you, I'm eating your chin chin. Are you using a Google? Are you using university mail? I don't know how you're not able to log in because it's very strange. Make sure you download the Google app. Okay, do the necessary thing by making it active. So you should be able to log in. Please, people should take this thing serious.
Ma, what time should we submit, ma?
We can submit now.
Sorry, I meant the deadline for submission.
It's 2 p.m. What of your Unilag mail? I don't know what to say, but everybody should be able to submit. And I don't know whether it's possible for somebody to submit for you. I don't know.
Hello, ma'am. The first question, is it show the synthesis of naphthalene and phenanthrene, or is it naphthalene and anthracene?
Phenanthrene.
Phenanthrene. Okay, ma'am.
Using Howard's method. Any other question?
The second question, ma.
Don't understand this. Yeah, go to the Google Classroom. You can see the question. I'm tired. Connect to the Google. The question is there. Osrep, I hope you've taken attendance. Make sure the attendance is well taken. This class elapses by 2 p.m. Like I said, Professor Sheku will be starting up tomorrow. As soon as she finishes the class, you'll be given just 7 days for you to go and read up and do your revision. Then we're going to have a comprehensive test. The test is going to be a physical test. If I were you, I would start reading now. The essence of the classwork for you to snap and share on Google platform is for you to have a copy of what you're snapping. So before exam or before test, you should be able to go through it and familiarize yourself with whatever. And my prayer for all of you that you end up with A or B. Nobody that have seen this course is not my friend. Okay, I should be able to leave the class, end the class, so finish up. You don't need this class to finish up your assignment. Thank you very much. Be available for physical class tomorrow, Professor Sheku. Please make sure you're available. People from Idiaraba, I beg you in the name of God, make sure you're available tomorrow for the class. I'm going to update you by 10 o'clock. Pastor, when is tomorrow's class? What time is tomorrow? What time is tomorrow's class? Nobody is talking. Unmute yourself and talk. What time is tomorrow's class? You guys are not ready for tomorrow's class. Very well then. Everybody is ready writing. You're ready writing for your assignment. Make sure you're available. I think I told her 11. So tomorrow's class is 11. So she'll be available by 11. So by 10 or by 9 o'clock, the deadline is 2. Deadline
Please,
is
ma,
2.
can you add 5 minutes, please? Because we are trying to submit on my end here, biochemistry department.
You still have 3 minutes.
Hey.
Just try and submit. Try and submit. Okay, thank you very much, everyone, for coming. I wish you the best.